Check it out now, y'all.
NanoHub U, online instruction.
Okay, so welcome back. This week we're going to explain the Schrödinger equation in one dimension. And before we do that, we want to make sure that this concept of wave-particle duality for light is very clear in everyone's minds. So the first lecture of this week is to discuss what the wave-particle duality means and to try and illustrate the consequences of it for both light and for particles. So to begin with, Young's two-slit experiment has already been discussed in the course. The premise for the experiment is reasonably clearly spelled out. You have a monochromatic light source. That monochromatic light source illuminates two slits that are closely spaced to one another. The slits, the distance between the two slits is some parameter d. And what you do is that you then observe the intensity of the light on a far screen. And what Young pointed out in 1803 was that the intensity distribution on this screen was not quite what was expected. Rather than seeing a uniform illumination, he observed these colored bands that filled up the entire screen. And he was able to explain the location and the intensity of those bands by assuming that light was a wave, and that light from one slit would travel and strike the screen and then either constructively or destructively interfere with light that passed through a second slit and also struck the screen. And the geometry for the equation that Young derived is sketched in this slide. It tries to make the case that if the screen is near to the slits, the geometry is very complicated. Young's derivation of the two-slit experiment relies on the fact that the screen is a far distance away from the slits, and when the screen is far distant away from the slits, then you've got two angles, theta and theta prime, that are essentially equal to one another. And this just simply means that the light rays traveling from the bottom slit at some angle theta is traveling parallel to the light passing through the top slit, traveling at another angle theta prime, which is essentially equal to theta. So this parallel ray condition is important for Young's explanation of the two-slit experiment. What Young points out is that whether you've got constructive or destructive interference is going to depend on the path length difference of the light that travels from the top slit compared to the light that travels from the bottom slit. So if the two light rays are parallel to one another, then you can draw a line perpendicular between these two light rays, and from the path length from B to point C is then going to be equal to the path length from D to point E. And the extra path length that the light follows traveling through the bottom slit is then just equal to this distance AD, which you can show by simple trigonometry is just equal to d sine theta. And so then the argument is that if this additional path length of the light through the bottom slit is equal to an integer times the wavelength of light, n lambda, then you've got the condition for constructive interference, or for a bright fringe that's observed on the screen, and that condition is just n lambda is equal to d sine theta. So this is Young's explanation for the observation of those bright and dark bands on the observation screen. And the explanation for that is treats light strictly as a wave. There's no question about it. Light has to behave as a wave in order to produce those bright fringes on the screen. It's a fair question to ask, are there any other reports of interference effects in light that would support this wave-like nature of light? And the answer to that question is yes, there's a number of different phenomena that have been discovered. One example is the thin film interference effect, where you've got a film of a thickness T, and if the thickness T of the film is comparable to the wavelength of light, then it's possible for light to reflect from the back side of the film, another ray of light to reflect from the front side of the film. If these two rays of light then constructively interfere after reflection, then you would observe a very bright condition for light reflected at that particular angle from the film. So this thin film interference effect was fashionable in the late 1800s, and it also supported the fact that light behaves as a wave. A completely new set of experiments was performed in the 1910 to 1915 time frame. This is when it became fashionable to direct X-ray radiation onto single crystalline solids and watch how the X-rays were reflected from those solids. Two people in particular were instrumental in starting this work. One was von Laue in Germany, and he discovered the diffraction of X-rays in 1912. And then in England, the same year, the Bragg father and son team also performed similar experiments. And these experiments also prove that light is a wave, right? In this case, the light is an X-ray. The X-ray is a very short wavelength electromagnetic wave, and the phenomenon of X-ray reflection from single crystals can only be explained by assuming that light behaves as a wave. So this technique is now used extensively to sort out the crystalline structure, the actual atomic positions, right, of atoms inside of crystals, and it involves an X-ray tube that emits a collimated beam of X-rays. Those collimated beams of X-rays strike a crystalline solid, and then there's going to be some sort of a detector or screen for observation. And what you see on this screen is dozens of bright spots which occur when the X-rays are constructively reflected from different crystallographic planes inside that crystal. So what's the basic physics? The basic idea is that if you have a crystalline solid with an incident X-ray beam onto it, some of that X-ray beam will reflect from the top layer of atoms in the crystal. Part of that X-ray beam will be transmitted and strike the second layer of atoms in the crystal. These two beams will then be reflected into a detector. And the same physics is involved. If the path length difference between, let's say, the top, the ray reflected from the top plane of atoms, if that path length difference is equal to an integer number of wavelengths from the X-ray beam that's reflected from the bottom plane of the crystal, then you're going to get a constructive interference effect, and that constructive interference effect is going to show up as a bright spot on your detector or on your photographic film. So the difficulty with the X-ray experiment, of course, is that there are many crystallographic planes that are possible. So if I just sketch out in 2 dimensions positions of atoms, and I imagine that there could be a plane of atoms designated by the topmost plane and the second plane, as I've indicated here, but there's also possibilities of multiple planes at different angles with respect to this obvious location of the first 2 planes. And all of these additional planes will have different spacings, they'll be oriented at different angles, and it just simply means that you could expect many possible directions of the X-ray beam to be scattered to produce this constructive interference. And of course that explains why there's all these spots that are observed experimentally on the screen. It's because those X-rays are reflecting off of multiple different planes in the crystal lattice. You can work out the conditions for constructive interference. The geometry for doing that is indicated here. This top black line represents the top row of atoms in a crystal. This lower black line represents the second plane of atoms in a crystal. The two planes are separated one from another by a distance d. There's an X-ray beam that comes in and strikes this top plane at some angle theta. And what you then have to do is you have to trace the trajectory of the X-ray beam that reflects from the second layer of atoms and compare the path it follows to the path that's traced out by the X-ray beam that's reflected from the top row, or the top plane of atoms. It's the path length difference between this red line and this blue line that are important, and the geometry for this is worked out on the slide. This is something you actually have to work through on your own. I provide all the geometry. The two critical triangles are the ones that are shaded in gray here, right? And what you have to do is you have to calculate this length here, the distance from A to B, and you have to compare it to the distance from R to D, right? And the geometry for that is worked, or the algebra for that is worked out. And what you find is you find the Bragg condition for constructive interference in this geometry is whenever the wavelength of the X-rays times some integer n is equal to 2d sine theta, where d is now the spacing between these crystallographic planes. So you pick up this additional factor of 2 compared to Young's double slit experiment, but otherwise the formulation looks very similar in both spirit and in algebra compared to the two-slit experiment. So there's a few comments that are worth making here. One is this is an oversimplified model for X-ray diffraction, but the law itself is correct. So the same law is derived using more complicated arguments that are physically more realistic. The second point is that for interference to occur, you're going to require incident electromagnetic radiation that has a wavelength lambda that's comparable to the spacing between these crystallographic planes, d. So since the spacing between planes of atoms in a crystal is something on the order of 0.3 nanometers, that's about 300 picometers, the incident electromagnetic radiation is going to have wavelengths also on the order of 300 picometers. And that implies the frequency of those incident electromagnetic radiation is on the order of 10 to the 18th hertz. So what I've just done is I've summarized a few experiments where light behaves as a wave. There's no other way to explain the experiments other than to say light acts as a wave. And if you listen to last week's lectures, I also described a few experiments where light had to be treated as a particle in order to explain the experimental data. And so I've prepared this very simple chart which tries to make the case that in some experiments light behaves as a wave, other experiments light behaves as a particle, and this is what is referred to as the wave-particle duality of light, right? It's puzzling why sometimes you have to treat light as a wave, other times you have to treat light as a particle or as a photon in order to get the correct answer. So this is a fundamental dilemma that sort of drove the entire area of modern physics in the late 1800s and early 1900s. And it leads to the next topic in the lecture, and that is the idea of matter waves that was introduced by Broglie in 1923. So Broglie was a theoretical physicist in France, and he started to wonder if it was possible for a particle to exhibit this interference-like behavior, this wave-like type of behavior that light exhibits. And of course, at the time, that was a very radical hypothesis, because everyone up until then had believed that a particle like an electron was a particle that had a mass m and had a charge e. There's no way it behaved as a wave, but that didn't stop the Broglie from thinking, and so he went through an argument very similar to the one that I've sketched out here. He said that the momentum of an electromagnetic wave is the energy U contained in that wave divided by the speed of light c. This is a result that Maxwell's equations predicted in the 1860s. According to Planck, the energy in an electromagnetic wave is Planck's constant h times the frequency of light, and so you can convert the frequency of light divided by the speed of light into a wavelength, and so you end up with this very famous formula that the momentum of a photon is equal to h, Planck's constant, divided by wavelength lambda. And de Broglie hypothesized that that same formula could be applied to particles, and in particular he said if a particle has got a momentum p, you divide p into Planck's constant h, and that tells you the Broglie wavelength of that particle. So that was a rather startling prediction, and of course once an idea like that is put forward, then experimentalists will try to prove one way or the other whether that prediction is, whether that idea is true or false. And Davison and Germer in 1927, they were employed by Bell Telephone Labs in New Jersey. They did a very, very famous experiment where they in fact proved that the Broglie was correct, that electrons do behave as waves under certain circumstances. And the experiment they did was an electron diffraction experiment where they took a beam of electrons, they collimated it by passing it through a narrow slit, right? They then allowed that beam of electrons to strike a single crystalline piece of material. The single crystalline sample consisted of periodic rows of atoms. The spacing between those atoms is on the order of 0.3 of a nanometer. And what they did is they looked at the reflected electrons from that sample. And what you might expect to observe is some sort of a diffuse pattern of electron reflection from the sample. But in fact, what Davison and Germer observed when they looked at a fluorescent screen was they observed very distinct bright spots in certain directions that were very reminiscent of the bright spots that are observed in X-ray diffraction experiments that we discussed earlier in this lecture. So they actually won the Nobel Prize for this experiment in 1937, and it was direct proof that these electrons, which are particles, can behave as waves and can undergo this constructive interference effect when they interact with matter. So today, this experiment is done routinely in labs throughout the world. It's referred to as low-energy electron diffraction. There's entire pieces of equipment set up in labs to do these experiments, and I just copied from the web a representative low-energy electron diffraction pattern from a single crystalline piece of material, just to show you that the reflected X-ray beam, or the reflected electron beams form a sequence of highly ordered spots. The order in these spots reflects the crystalline symmetry of the atoms that the electrons are reflecting from. And the only way you can explain this result is that the electrons are interacting with the crystalline substrate as if the electrons behave as waves. If you like to do simulation experiments on the web, I give you a website here where you can go and you can simulate Davison and Germer's famous experiment. So this is an electron gun. You can fire electrons at a periodic array of atoms, and you can watch the direction of the electron beams in certain directions where constructive interference sets up. You can actually watch that build up in the process of the simulation. And then the last thing I wanted to mention was the the attempt to do a two-slit experiment with electrons. In other words, try to mimic Young's experiment with light, except do the same experiment with electrons. So this is a technically challenging experiment because it requires you to take an electron source. You have to direct that electron source onto two slits that are closely spaced apart, and then you have to have a screen which is sensitive to electron intensity. In other words, where the electrons strike the screen. And if electrons behave as waves, you would expect that the pattern of electrons striking the screen would somewhat resemble the pattern that Young saw when he did the two-slit experiment with light in 1803. So there have been a number of attempts to perform this experiment. If you like to read the original literature, there's a nice discussion in 1989 in the American Journal of Physics. I just refer you to that. If you're more into web-based discussions, there's been a recent discussion of this two-slit experiment in March of 2013, and I give the website. And here I've just copied the intensity of the electron beam as it strikes the screen over time. So initially, very few electrons strike the screen. As the electron source is left on for a longer and longer period of time, what you see is you start to see a distinct banded pattern of electrons, and this banded pattern resembles Young's two-slit experiment with light. It's very, very nice correlation. And again, it just proves once again that these electrons do in fact behave as waves under certain circumstances. So this idea that the Broglie put forward is an important idea because it gives you a sense of when electrons behave as waves and when they behave as particles. I tried to summarize that sense in this slide where I say if the electron, which has a mass m, if that electron is confined in a region of space with a dimension, a characteristic dimension L1, and if L1 is considerably larger, than the Broglie wavelength lambda of that electron, then that electron is going to behave as a particle. Conversely, if you take that same electron and you put it in a very narrow box, where now the confines or the dimensions of the box, L2, are comparable to the Broglie's wavelength lambda, then in this configuration, the electron behaves as a wave. So this Broglie wavelength sort of provides a confinement boundary that allows you to distinguish when you have to treat electrons as waves, when you have to treat electrons as particles. And we'll see this over and over again throughout the semester. So this is a reoccurring theme that you have to be aware of. The final slide is just an attempt to summarize this lecture in words or in pictures. I tried to show the dual character of light and electrons in a parallel way. And I tried to make the case that if light is passing through large objects like lenses, then you can treat the physics of that by treating light as rays. These are straight line particle trajectories that you can trace out, and you can understand all kinds of things about image formation. On the other hand, if you start to take that same light and pass it through slits, where the separation or the width of the slit is comparable to the wavelength of light, then you have to start to treat light as a wave object. You have to rely on wave-like behavior. Same thing happens for electrons. If you take an electron of mass m, put it in a box, if the dimensions of the box are large compared to the Broglie wavelength, then that particle is probably going to behave as a classic particle with a mass. If, on the other hand, you let that same electron start to interact with objects where the separation between the objects d is comparable to the Broglie wavelength of that electron, then you're going to have to treat that electron as a wave. So hopefully this simplistic summary tries to explain the two limits in this wave-particle duality paradox that plagued a lot of experiments in the late 1800s and early 1900s. And what we'll do in the next lecture is we'll try to we'll start to think about how to derive an equation that explains the motion of these de Broglie waves in space and time. So that'll be called the Schrödinger equation, and that'll be the topic of our next lecture. Thank you.